Okay, so we are in Statistical Rethinking, second edition. We're in chapter 9, and we're on the very last problem of chapter 9. We're on 9H7. Okay. This chapter has been all about kind of different algorithms that might be used to solve some of these Bayesian problems, and this last one here is on Hamiltonian Monte Carlo. Now, in the previous few questions, I think that we have been trying to code different versions, or kind of bespoke versions of the Metropolis algorithm, and now we are going to code, with a cheat function, the Hamiltonian Monte Carlo. Okay, so there is an example in the book that goes over, I can't remember what data set, but it is a different data set than what we are approaching in this problem. So in this problem, we're going all the way back to, well, what is it, chapter something or another, early chapters, maybe 2 or 3, where we are looking at the globe tossing data. Okay, so if you remember, the idea is that we have a globe amongst a bunch of people, and we're tossing it back and forth, and every time that we catch it, we look at where our index finger has landed, and if it's on water, we mark water, and if it lands on land, then we mark land, and we're using this as a way to try to approximate how much of the globe is covered in water versus land. Okay, so the example that is given in the chapter is actually done on, give me a second here to find it. Okay, yeah, so it's done on normal distributions, and so it goes through the math and does all that for you. But the globe tossing model is binomial. It's a binomial data. Okay, so that's where the change is. Okay, so let's just get into it. So let me come here first to the code. Okay, so the first thing that we need to do is to define a couple of functions. One the book calls u, and so we'll just continue to call it u. And this is the negative log probability of our probability distribution. Okay, so now you can go through and you can derive, that's what I've done here, the negative log probability distribution of a binomial distribution. Okay, but you don't have to worry about that really, because we can use R to do this. Okay, so in R, okay, so notice I'm wrapping all of this into a function, right? So I'm going to return the negative log probability space here. Okay, but I just take my d binom, so the density of binomial distribution, and I just define what I want. Okay, so y is the number of I think water, size is the number of or n is the number of tosses that we had, and then the probability. Okay, so the probability of I guess water in this case. Okay, and that's going to be defined by q in the function, right? And so we'll go back later and we'll mess with q. But for right now, q is just a placeholder. And then this is the very convenient part of using R instead of having to calculate all by hand, is we have this option of saying, do we want the log density or the non-log density? And we can just say log density equals true. Okay. Now, because this is a Bayesian approach here, right? We also need the prior, right? This is just the likelihood, right? This is just giving us the likelihood, and we need a prior. And I believe that in that question, the prior was just a flat prior, right? That anything between 0 and 1%, or I'm sorry, 0 and 100% could be water, and that was our prior. Okay, so now in log land, so in the Bayes formula, we're usually multiplying the likelihood and the prior, right? But in log land, multiplication becomes addition. So here we just add, and this line down here represents the prior, right? So it's just a uniform distribution between 0 and 1, and again we signify that we want the log probability, okay, the log density. And then again, so that gives us the log probability distribution, and we want our function to return the negative log probability distribution. So we just return negative of all of this. Okay, good. So the next function that we need is the gradient function, right? So this right here defines some kind of landscape, okay? And we want to know the derivative at any point on that landscape so that our algorithm knows which way to, to go across this negative log probability space. So again, you can derive this, right? So you can find the gradient here, okay? And so you just take the derivative of this function u, right, with respect to p, right? And we come out with all of this right here. I think that this would be a little bit more complicated if we had a non-uniform prior, a non-flat prior. But anyway, that's what we're assuming, and this is what we come out with. So we can just hard code that directly into our function here. Okay. And now I just need to define the data. So 9 tosses and 6 of them are water. Okay. So now this is the function here. Okay. So this this is how we're going to make our Hamiltonian Monte Carlo run. Okay. So when we go through this, so we have so when we go through this, so I'm more or less adapting what is in the book here. Okay, but we start with our list that we initialize at a beginning probability, and I'm just putting it at 1/2, right? So again, our probabilities of water can be anywhere from 0 to 1, so 1/2 seems like a good idea. I need some number of samples, okay? And so we're going to run this for 25 iterations, and that's what we have here. And well, anyway, so you can kind of go through the code. Now, earlier I said that we're kind of using a cheat function that's part of R, and that's this HMC2, okay? Now, the book, in one of the overthinking sections on page 276 kind of shows what this function is made of, but we're just using this function. But anyway, the rest it really can just be copied from the book and adapted a little bit. So anyway, what you come out with is your trajectories, okay, of the Hamiltonian Monte Carlo. So this is the number of iterations across here, and then P is, in fact, I don't like time in there. I think I'd rather that say iterations. Okay, but we can run this and we get our sample path, right? So P is the parameter that's being estimated at each iteration as we go along here. Okay, so that is it for this one.